Good morning. Today we'll be talking about the Ocd approach for checking the reaction conditions in electrocyclic reactions. But before we do that, let's recap the electrocyclic reactions. If you remember, electrocyclic reactions were those reactions in which you had an open chain polyene system having k pi electrons which underwent a reorganization of pi electrons to form a cyclic system having 2 pi electrons less than the reactant, that is k minus 2 pi electrons, and mu sigma bond was formed. And even if you remember the stereochemical modes of derivative here, there were 2 stereochemical modes. One was, if you remember, the terminal lobes of the polyene system rotated in the same direction. Then we said this is called rotatory. And if the terminal lobes of the polyene system rotated in different direction, then we said it is disrotatory. We call this as con, and we used to call this as dis, conrotatory and disrotatory mode of electrocyclic ring opening and closures. Now, in order to understand the Ocd approach for these electrocyclic reactions, we need to understand that which symmetry operation is to be chosen for which stereochemical mode. Now, in order to understand this thing, let's take the simplest example of this butadiene cyclobutene interconversion. Now, if I draw the butadiene, I know butadiene molecule is this molecule. If I look at the terminal lobes of butadiene, it is this. If this molecule has to undergo, let's say, a ring closure in such a way that both lobes are moving in the opposite direction, that means I'm talking about both lobes are moving in the same direction. Let's say I'm talking about a conrotatory ring closure. Then in order to have an effective bonding overlap, if this is plus and if this is moving in this direction, this lobe should move in this direction only. If this lobe is moving in this direction, the upper lobe is moving towards this side and the lower part of this lobe should move like this. In other words, the upper phase or the upper lobe of the first p orbital and the lower p lobe of the second p orbital should interact in a conrotatory ring closure. That means both should have similar signs in order to have a bonding overlap. Means to say that whenever you are expecting a conrotatory ring opening or closure, largely speaking, we are expecting that in the case of the conrotatory ring closure, we'll be having the opposite signs, the crisscross kind of a similar signs should be encountered. Therefore, the symmetry which conserves this kind of a opposite similar sign natured orbital is the C2 symmetry. Why? Because if I operate, or let's say if I perform a C2 operation on this kind of orbital which should undergo conrotatory ring closure in order to have bonding overlap, then I could encounter a similar kind of an orbital. Why? Let's say if I have to perform C2 in this, where will the C2 be performed? Along this axis in the molecular plane. You rotate this molecule, this lobe will become this one, this will become this one, this will become this one, and this will become this one. And this is 1, 2, as you remember, we used to perform C2, what will happen? My product will be this one. 1 will become 2, 2 will become 1, and 1 positive will come down, negative will come up. The seconds positive will come up and seconds negative will come down. You see both orbitals, pick one, place it over here. Both orbitals are symmetry, are having similar, encountering similar signs. Therefore, this C2 axis of symmetry in a conrotatory ring closure is the chosen a symmetry property because it conserves the orbital in this fashion. I repeat again what I'm saying. I'm trying to say here is that when you're using a conrotatory ring closure, that means the upper face of the first lobe and the lower lobe of the second lobe have to interact. That means these two have similar signs. Now, since these two have similar sign, it is the C2 operation which conserves this kind of an orbital. Hence, while undergoing or while choosing a conrotatory ring closure, we normally prefer a C2 mode of the ring closure. Similarly, if we talk about the disrotatory process. Now, in distributory process, again taking the similar example of cyclobutene or butadiene interconversion, let's say if I'm choosing a distributary process. Now, for distributary process, both lobes are moving in opposite direction. If this lobe is moving in, let's say, clockwise direction, this lobe has to move in an anti-clockwise direction. If this is, let's say, positive, again this has to be positive in order to have bonding overlap. Now, if I perform a mirror symmetry on this, where do I pass the mirror? Like this. If I pass this mirror plane, then I produce the similar kind of an orbital. That means the symmetry is conserved when you use the mirror plane of symmetry operation while undergoing a distributory ring closure. Therefore, the symmetry is conserved. Now, if I had alternate things, now first of all, let's repeat what I've said. In order to, when we are encountering a distributory ring closure or opening kind of a reaction, then in that particular case, you see that the terminal lobes same face has same sides. That is why the bonding overlap will occur. If this is positive, this has to be positive. Now the operation, the symmetry operation which conserves the symmetry is mirror. Had we undergone a C2 operation on this one, what would have happened was this plus would have become plus here, this minus would have become minus here. That means then the operation would have created an anti-symmetric orbital. Therefore, while working out the OCD approach for electrocyclic reactions, the most important point we need to consider is that the stereochemical mode which we are choosing will correspond to a particular symmetry operation. If we are discussing quadratic ring closure or opening, we choose always the C2 axis of symmetry, and if we are taking, let's say, discussing the distributory mode of ring closure or opening, then always we'll choose the mirror plane of symmetry. And as I've told you, the reason for this is that in the case of quadratic, it is the C2 which conserves the symmetry. In the case of distributory, it is the mirror which conserves the symmetry of the orbital. Right. Now, if you have understood this thing, let's try to exemplify the various possibilities of this reaction. We'll start with the first example. Again, this example is butadiene cyclobutene interconversion in the case of electrocyclic reactions. My butadiene molecule, of course, is this one. It undergoes electrocyclization. We know we used to move the bonds in this fashion. It underwent electrocyclization, forms cyclobutene. Now, as in the OCD approach, we need to work out that what bonds in the reactants are breaking and what bond in the products are forming. Now, there are 2 pi bonds in the reactants which are breaking. Therefore, 2 pi bonds, that would mean 4 pi electrons are involved in the reactant system. Corresponding to 4 electrons, you should have 4 pi molecular orbitals, and out of those 4 pi molecular orbitals on the reactant side, 2 pi should be bonding and 2 pi should be anti-bonding molecular orbitals. This is simple. Now, if you look at the product side, you have this new sigma bond which is formed and this new pi bond which is formed. Therefore, the product side should have 1 pi bond formation and 1 sigma bond formation. Corresponding to 1 pi bond, you should have 2 pi electrons, 2 pi molecular orbital, 1 pi should be bonding and 1 pi should be anti-bonding in nature. And similarly, corresponding to the sigma bond, you should have 2 sigma electrons which should correspond to 2 sigma molecular orbitals. 1 sigma should be bonding and 1 sigma should be anti-bonding. So I have understood that which orbital system should be there in the reactant as well as in the product. Now, if you look at this particular reaction, therefore I need to draw 4 molecular orbitals corresponding to the reactant. I need to draw 4 molecular orbitals corresponding to product. We've already drawn the molecular orbitals corresponding to butadiene, so I'd not waste time and straight away draw. I'd write the reactant here. If I draw the orbital diagram, and I'll write product here. Reactant is what? Butadiene, and product is what? Your cyclobutene. I need to draw 4 molecular orbitals. Let's draw those 4 molecular orbitals on the reactant side. 1. Let's draw the 4 lobes here. 2. 3. And of course the 4th one. Remember, the butadiene's 4 orbitals were what? Psi1, Psi2, Psi3 star and Psi4 star. This was of course the axis of energy. right? This corresponded to the zero value of energy. That would mean that these orbitals were the bonding molecular orbitals and these molecular orbitals were the anti-bonding molecular orbitals, if you remember, right? Again, putting the nodes, psi 1 should have 0 node, psi 2 should have 1 node, psi 3 should have 2 nodes, and psi 4 should have 3 nodes, right? 0 node, 1 node should come in the center, 2 nodes should come here and here, 3 nodes should come here, here, and here. This is simple. Okay, that means no node means the upper phase should have same signs in all the orbitals. 1 node means plus plus, node comes, sign changes. We should be having this one. 2 nodes means plus, sign, node comes, sign changes, node comes, sign changes. This should be the orbital. Finally, when there are 3 nodes, all the upper lobes should be having anti-bonding interaction with one another. This is how the molecular orbital of the reactants should assume to look like. And if you look at and compare it with the product side, now in the product side we have 4 molecular orbitals. Now let's go back to what we had on the product side. On the product side we had 4 molecular orbitals, 2 corresponding to sigma, 2 corresponding to pi, and we know sigma bonding is always more stable than the pi bonding. That means on the reactant side, in the ground state, on the bonding molecular orbital side, we should have 2 molecular orbitals, one sigma bonding, one pi bonding, and sigma bonding should be more stable than pi bonding. On the anti-bonding side, we should have 2 molecular orbitals, sigma anti-bonding, pi anti-bonding, and I know pi anti-bonding is always more stable as compared to the sigma anti-bonding. Therefore, the choice is very clear that while drawing the product side, the first orbital which we need to draw, going from down to up, the first orbital that we need to draw should be one which is sigma. And which sigma orbital are we talking about? The one which is formed, this one. So I draw the sigma orbitals like this sigma orbital, this one. I'm not referring pi. So this is the first orbital. The second orbital is the one in which you should have a pi molecular orbital. That means this node. Which one was the pi, if you remember? Pi was this orbital. Okay. The second is the pi orbital. So this is, let's say, sigma 1, or you can call it as phi 1, and let me call this as psi 1. Okay, or you can simply call it, because it corresponds to 2 electrons of your ethene, let me call it as pi 1. Corresponding to the anti-bonding side, pi star was more stable. You can call this one orbital. This is what? Pi 2 star. And the least stable orbital was the one which was the sigma anti-bonding. Therefore, I'll draw the sigma anti-bonding like this. This is what? Phi 2 star. Okay. Corresponding to sigma, this has 0 nodes. Corresponding to sigma, the highest orbital was 1. This is 1 node. Corresponding to pi, the first orbital has 0. Corresponding to pi, the first orbital has 1 node. Where do we draw the nodes? Here this has no node, that means we have bonding overlap here. Here there is no node, that means we have a bonding overlap here. Here there is 1 node, that means the 1 node will be coming here. You have positive sign, you have negative, negative and positive. Here you have 1 node, that means positive will be interacting with negative. That's why there is a anti-bonding overlap. So we've drawn the molecular orbitals of the reactant and we've drawn the molecular orbital of the products, considering which orbitals were formed, which bonds were formed and which bonds were broken. So we've drawn the reactant molecular orbitals, we've drawn the product molecular orbitals. The next thing which is needed to gauge this reaction, to gauge the reaction conditions of this reaction, would be to work out the symmetry, or to assign the symmetry operation onto these molecular orbitals. So what we'll do here is we'll assign both symmetry operations, mirror as well as C2. If you remember what I've just told you, that mirror symmetry operation should correspond to a distributory ring closure or opening, and the C2 symmetry operation should correspond to a contradictory process. Okay, we'll apply both mirror as well as C2 operation here, mirror and C2 on this thing. Okay, if you look at mirror, the mirror should pass from here, somewhere from here. So this is the mirror plane of symmetry. Keep your hand here or your pen here. Positive is encountering a positive sign, positive is encountering a positive sign. And if you remember what I told you, that for a similar kind of an orbital system, for a Pauline system, if this orbital is, let's say, having one symmetry operation, the upper orbital would have the opposite. It should be anti-symmetric, it should be symmetric, it should be anti-symmetric. You can check it for yourself. Positive encountering negative, anti-symmetric. positive encountering positive, negative, negative is symmetric, positive, negative, negative, positive, anti-symmetric. So you can have an alternating symmetry. And same will be the case for C2 also. Now, in order to work out the C2 symmetry, what we used to do, if you remember, we used to check the crisscross, relationship or the diagonal relationship. Positive is encountering negative, right? This positive is encountering negative. This is anti-symmetric. Positive encountering, this is positive here. Positive encountering positive, this is symmetric. Positive encountering negative, anti-symmetric. Positive encountering positive, symmetric. Again, see, the relationship is an alternating relationship. Similarly, we assign the symmetry operation onto the product side also, C2 as well as mirror. Okay, let's start with the mirror operation. Again, the mirror will pass through this. So positive comes in front of positive, that means it is symmetric. If this is the the sigma orbital, the next sigma orbital, that is this one, will have opposite symmetry. Therefore, if this is symmetric, this orbital should be anti-symmetric, right? Look at this orbital, pass a mirror through this. Positive is encountering a positive sign, therefore it is symmetric. Positive is encountering a negative sign, therefore it is anti-symmetric, right? So we've we've applied the symmetry operation. Of course, this is the mirror plane we are talking about, right? Let's apply the C2 symmetry. Now, while applying the C2 symmetry on a sigma orbital, see, the sigma orbital is something like this. You apply C2. Where will the C2 be applied? C2 is here. Like, consider my pen as C2. C2 is like this. And then you rotate this pen at an angle of 180 degrees. This thumb will come this side and this thumb will come this side. That means positive will come here, this positive will come here. So we're encountering the same signs, and if we are encountering the same signs, you lift the new orbital, place it out on the first orbital or the older orbital. If it is encountering similar signs, we say this is symmetric. Hence, on applying C2, you pass an axis from this side, rotate this orbital will come here, this orbital will come here. That means positive will be positive only, this positive will be positive only, therefore this operation is symmetric. And consider the next sigma orbital, which was this one. If you pass a mirror on this thing along the molecular plane, this positive will come here, this negative will come here. That means the molecular orbital will be constructed, will have negative here and positive here. That molecular orbital, once placed on this one, would encounter different signs, therefore it should be anti-symmetric, right? And this is simple. Positive encountering negative in the diagonal relationship, anti-symmetric. Positive encountering positive in the diagonal relationship, symmetric. So that is how we have assigned symmetry operations, both mirror as well as C2, onto a butadiene cyclobutene conversions molecular orbitals, right? The next thing is, now apply these, let's draw the orbital correlation diagrams for the confirmatory process as well as for the distributory process, right? Now, while drawing the orbital correlation diagram, let's first of all work out on the condensatory process. Now, while doing this condensatory process, I know that in a condensatory process, the terminal lobes are moving in the similar directions, and the symmetry operation which is chosen, or the symmetry operation which is referred to is C2, right? Let's draw the orbital correlation diagram first under thermal conditions, where we are not exciting the electrons from the ground state to the excited state. Condensatory process first under thermal conditions. Okay, my reactant is what? Butadiene, and my product is what? Cyclobutene. So I draw butadiene here, I draw cyclobutene here. This is my reactant system. I'll just draw the orbital Psi1, Psi2, Psi3, Psi4. This is my reactant side. Psi1, Psi2, Psi3 star, Psi4 star. While drawing the orbital correlation diagram, I'm not actually drawing the orbital, so it becomes easy and simple for me to draw this thing. And on the product side, if you remember, I had Phi1, Phi1 star, Phi2 star, Phi2 star. So Phi1, Phi1, Phi2 star, and Phi2 star. Which symmetry operation has to be chosen? C2. And corresponding to C2, if you remember, let me remember, corresponding to C2, what was the symmetry concentrations of the product? when I'm taking reactant, that is butadiene system, the lowest orbital was antisymmetric, symmetric, antisymmetric and symmetric. So the shape of the orbital is something like this. The shape of the orbital is something like this. So it is antisymmetric, symmetric, antisymmetric and symmetric. As far as the product is concerned, this was symmetric, antisymmetric, symmetric and antisymmetric. Now let's check the correlation. As per as the Woodward-Hoffman law of conservation of orbital symmetry, we need to check for thermal conditions. We need to correlate the ground state reactant orbitals with the ground state product orbitals. And if you correlate here, see, A correlates with A, S correlate with S, that means ground state is matching, even though if it's not a direct matching, even if it is crisscross matching, but the total reactant molecular orbital symmetry and total products molecular orbital symmetry in ground state. This is the ground state, of course, and this one should be the excited state, is matching. Since it is matching, I can use this word that phi 1 2 phi 2 2 correlates with phi 1 2 and pi 1 2. Hence, this process is thermally allowed. Right? Which process? Contact process. Under which reaction conditions? Thermal reaction conditions. Now let's check the same process under photochemical conditions. Now, while doing photochemical conditions, my orbital correlation diagram would look and appear to be it would look similar only. It will not be looking different. So what I need to do while drawing the photochemical condition is, again, on the left side I have to draw the reactant. On the right side I have to draw the product. Again, my reactant is what? Butadiene. My product is what? Cyclohexene. Again, draw the OCD approach. Let's say this is the energy axis. Draw the OCD approach. Phi 1, phi 2, phi 3, phi 4. The reactant molecular orbitals. Phi 3 star, phi 4 star, the zero value of energy corresponds to ground state. This corresponds to the excited state. Okay, and on the product side I have phi 1, pi 1, pi 2 star and phi 2 star. So it is pi 1, pi 1, pi 2 star and phi 2 star. And remember, the symmetry operation assigned to a quantitative ring closure, whether it is undergoing a thermal process or a photochemical process, would always remain C2. Okay, and if you remember the symmetry operation is C2, then the orbitals symmetry operation, whether we are talking about thermal condition or photochemical condition, should be same. Therefore I can draw the same one for this. So it is AS here, and for the product side it was SA. Now once we have excited, let me also draw the electrons here. 2 electrons should have come here, 2 electrons should have come here because it was a 4 electron system, 2 electrons should come here, 2 electrons come here because it was a 4 electron system. Under thermal condition, that is ground state was only populated. Now once you talk about the excited state, there were 2 electrons here, 1 electron from this orbital jumped to this one, 2 electrons here, 1 from this orbital jumped to this one. So we are correlating or matching up to the first excited state, and once we correlate up to first excited state, A matches with A, S matches with S, but here look at this one, A and S, there is a mismatch. That means the total reactant orbitals symmetry and total products orbital symmetry do not correlate up to first excited state. Hence this process is photochemically forbidden. And I'd say phi 1 2, phi 2 1, pi 3 star 1 do not correlate with phi 1 2, pi 1 1 and pi 2 star 1. Hence this reaction is photochemically forbidden. Alright, so this is how we gauge the reaction for electrocyclic reactions. All we need to do is to work out the molecular orbitals of the reactants. We need to work out the molecular orbitals of the products. we need to assign a symmetry operation. In the case of electrocyclic reaction, it is simple. If you are following a conrotatory process, it should be the C2 axis. Assign the C2 symmetry operation on all the molecular orbitals. Correlate ground state if they match, it is thermally allowed. Correlate up to first excited state if they match, reaction is photochemically allowed. Let's do the same thing for a distributary process also. Let's do the same thing for a distributary process. I am doing the same reaction but now for a distributary process. And first condition I should know is that the symmetry operation that we choose for a distributary process is which one? The mirror plane of symmetry. If this thing is all right and simple, then first we'll talk about the distributary process under thermal conditions. And the only difference between thermal and photochemical conditions is that in thermal condition it is the ground state which is populated, and in photochemical conditions up to first excited state is populated, right? The reactant system remains same. My reactant side is butadiene and my product side is cyclobutene. Reactant side is butadiene, product side is cyclobutene. I need to draw the molecular orbitals corresponding to your cyclobutadiene and butene. Okay, for a reactant side it is phi 1, phi 2, phi 3 and phi 4. These were the 4 molecular orbitals. Phi 3 star, phi 4 star, this was the 0 of energy. So this was the 0 of energy. This corresponded to ground state, this corresponded to the excited state, right? While drawing the molecular orbital of the product, I had phi 1, pi 1, pi 1 star, phi 2 star, this was it, and phi 2 star. And then the symmetry operation which was chosen was mirror, and if you remember in mirror, you can see back also, if you remember in mirror, this was symmetric and alternating. This was symmetric, this was alternating, this was symmetric, this was alternating. This was the symmetry operation. Now, under thermal conditions, since we are in the reactant system taking 4 electrons, I have to accommodate 4 electrons, 2 will come here, 2 will come here, excitation will not occur. Similarly, in the product system, you'll have 4 electrons, 2 will come here, 2 will come here. Now, let's match the symmetry property. S correlates with S, perfectly alright, but here, this O do not correlate with S. That means the ground state reactant orbitals and the ground state product orbitals are not correlating when a distributary process is followed. Therefore, we can say and we can write that phi 1 2, phi 2 2 do not correlate with phi 1 2, pi 1 2. Hence, this process is thermally forbidden. Which process are we talking about? The distributary process under thermal conditions, right? Similarly, we talk about the distributary process under photochemical conditions. And under photochemical conditions, everything remains the same. The reactant molecular orbitals, the product molecular orbitals, even the symmetry property remains the same. The only difference is that one electron from the ground state will get excited to the first excited state. So I'll draw the molecular orbitals again. This example which I'm drawing, I'm trying to, put everything into it. I'm not trying to leave anything, which should not be written. And in examples to come, I can probably skip certain parts and we can jump on with the conclusions. Anyways, I have 4 molecular orbitals again here. Phi 1, phi 2, phi 3 star, phi 4 star. Simple, the 0 value of energy corresponds to ground state. This corresponds to the excited state. Right, on the product side, I have phi 1, I have pi 1, pi 2 star, phi 2 star, phi 1, pi 1, pi 2 star, and phi 2 star. Again, same symmetry operation, that is mirror. It was S, A, S, A, this was S, A, S, A. Since it is photochemical condition, 1 electron from psi 2 should jump to psi 3. Similarly, 1 electron from the product side from pi 1 should jump to pi star 1. So this is my electronic consideration. This is my electronic consideration as far as the product is concerned. Okay, now let's match the symmetry. S matches with S. Since we have to match up to first excited state, A matches with A, S matches with S. Therefore, even if it is a crisscross matching, still the reactant molecular orbitals and product molecular orbitals correlate up to first excited state. Hence, we can say phi 1 2, phi 2 1, phi 2 1 and phi 3 star 1 correlates with phi 1 2, pi 1 1, pi 2 star 1. Hence, this reaction is photochemically right. So we worked out that for a distributory process, the reaction can be thermally, for example, in the case of butadiene cyclobutadiene anticonversion, this is thermally forbidden but photochemically allowed, but in the case of condensatories it was thermally allowed and photochemically forbidden. So this is how we work out the explanations of the OCD approach in using the electrocyclic reaction. I'll repeat again what we have done. It's a simple correlation. We need to draw the molecular orbitals of the reactant, need to draw the molecular orbital of the products corresponding to the bonds which are broken and the bonds which are formed. Once we've drawn the molecular orbitals, then in the case of electrocyclic reaction, the mirror plane conserves the distributory process, whereas the C2 axis of symmetry conserves the condensatory process. Hence, we need to assign the mirror operation while considering the condensatory process, and we need to draw the mirror operation while considering a distributory process, and we need to apply the the C2 axis of symmetry while considering a condensatory process. Now, once the molecular orbitals are drawn, the symmetry property has been assigned, then we can check the symmetry up to ground state or up to first excited state. If it matches up to ground state, that particular electrochemical stereochemical mode is allowed under thermal conditions. If it correlates up to first excited state, that particular stereochemical mode is allowed under photochemical conditions. That is the method of gauging the reaction conditions. We'll take the second example of the electrocyclic reactions, checking out the reaction conditions using the OCD approach. This example is the hexatriene cyclohexadiene interconversion. We know hexatriene is a 3 pi bond 6 pi electron system. This undergoes electrocyclic ring torsion. You know how to form the product. We just need to move the bonds, and once you move the bonds, you'll end up with the formation of this cyclohexadiene system. Now, considering the reactant side, which bonds are broken? As you can see, these 3 pi bonds are involved. So 3 pi bonds are involved, or they are broken, and these 3 pi bonds corresponds to 6 pi electrons. That means 6 pi molecular orbitals are formed, are there which are involved, out of which 3 will be bonding and 3 will be anti-bonding. And conversely, if you talk about the product side, which new bonds are formed? As you can see, 2 new pi bonds are formed and 1 new sigma bond is formed. So these are the 3 bonds which are formed. Corresponding to the 2 pi bonds which are formed, we will have 4 pi electrons and therefore 4 pi molecular orbitals, out of which 2 will be bonding and 2 will be anti-bonding. Of course, pi. So 2 pi will be bonding, 2 pi will be anti-bonding. And if you consider the sigma bond, since 1 sigma bond was formed, that means 2 sigma electrons, that means 2 sigma molecular orbitals, out of which 1 sigma will be bonding, 1 sigma will be anti-bonding. So it is very clear that if you look at the product side, there will be 3 molecular orbitals corresponding to the bonding and 3 molecular orbitals which will correspond to the anti-bonding region. Out of the 3 molecular orbitals, 2 bonding will come from pi and 1 bonding will come from sigma, and in the anti-bonding side 2 will be coming again from the pi and 1 will be coming from sigma. Again, what we have used previously also, we've always said that sigma bonding is always more stable, therefore lower in energy as compared to pi bonding, and conversely pi anti-bonding is always more stable as compared to sigma anti-bonding. Therefore, positioning these orbitals on the energy axis should not be difficult. Okay, now next step is to draw the orbitals for the reactant as well as products for the electrons or the molecular orbitals which are involved, right? Now my reactant side is, as you can see, a hexatriene, and my product side is cyclohexadiene. Because of the scarcity of the space, I've written it here. Okay, now therefore since I had 6 electrons or 6 molecular orbitals corresponding to hexatrine, I need to draw these 6 molecular orbitals. So what I've done is I've drawn those 6 molecular orbitals, psi1, psi2, psi3. I've not written nodes as of now. I'll just write it psi4 star, psi5 star, psi6 star. These are the 6 molecular orbitals corresponding to the hexatrine. Of course, this should be the zero value of energy. This region should correspond to bonding molecular orbital, or it is the ground state. This region from psi4 star onward should correspond to the anti-bonding molecular orbital, and it is the excited state. How I have drawn the 6 molecular orbitals, just have written the lobes. Now I'll try to put the node. Psi1 is having 0 nodes. That means no nodes would mean that all the upper face lobes will have the same sign. And as customary, we normally write the upper face with the positive sign. When there is one node will come in the center, so it is plus, 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 minus, minus, minus. This is the shape of the orbital, which is psi1. Okay, psi3, 2 nodes. Try to put nodes so that there should be symmetric cleavage. So it is positive. Positive node comes negative. Negative node comes positive. Positive. This is my atomic orbital. Okay, let's go to psi4 star. There should be 3 nodes. Again, a symmetric kind of a cleavage. So I've cut it like this: plus, minus, minus, plus, plus, and minus. Right? Psi5 star and psi6 star. Psi5 star should have 4 nodes. 4 nodes should come here, 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 and here, so that there should be a symmetric cleavage. So if it is plus, this would be minus, plus, plus, minus, and plus. One thing you should always notice while drawing the nodes is when you have even nodes, see 0, 2, 4, the terminal lobes same face always has the same sign. For example, psi4, even nodes, terminal lobes same face has same sign. The upper face has plus signs. Consider psi2 having 2 nodes, psi3, upper face has same sign. Psi0s, even nodes, upper face has same sign. And conversely, if you have odd nodes, the upper face will have opposite signs. For example, psi2, which has 1 node, upper face will have opposite sign. Psi4, which has 3 nodes, will have opposite signs. And similarly, psi6, which have 5 nodes, should have opposite sign. How? 1, 2, 3, 4, 5. This is how we'll put the nodes. This is plus, this becomes minus, plus, minus, plus, minus. Okay, this is the shape of my atomic orbitals of the reactants. Alright, now I need to assign them the symmetry operation. You remember, when using the electrocyclic reactions, the mirror plane corresponds to a distributory process, whereas the C2 symmetry operation should correspond to a commutative process. But as customary, I'll write the symmetry operation corresponding to both of them. Okay, I'll start from the psi1 orbital. Mirror plane, what mirror plane are we taking? We should pass a mirror from here, and it should bisect the molecule. Should be in the plane perpendicular to the molecular plane, and while checking the mirror plane positive is encountering positive, this should be symmetric. And as I've told you before, similar kind of molecular orbital should have alternating symmetry. So this is symmetric, anti-symmetric, symmetric, anti-symmetric, symmetric, anti-symmetric. So you can check for yourself. Opposite signs are encountering positive, is encountering negative, that's why it is anti-symmetric. And for C2, you check the diagonal relationship. Plus is encountering minus, that means it is anti-symmetric. And again, there is an alternating symmetry. This is anti-symmetric, this should be symmetric, anti-symmetric, symmetric, anti-symmetric, and symmetric. So we have drawn the molecular orbitals corresponding to the reactant. We have drawn the molecular orbitals corresponding to the products. Now we will draw the molecular orbitals corresponding to the product. Okay, in the product side, let's go back again. In the product side, 1 sigma bond was formed, 2 pi bonds were formed, 4 electrons or 4 molecular orbitals contributed by these 2 pi bonds, 2 electrons or 2 electrons coming from the new sigma bond which is formed. Therefore 2 molecular orbitals are contributed. Again, as I've told you, in the bonding side, 2 molecular orbitals were coming from the pi molecular orbital, and 1 was coming from the sigma molecular orbital. Right, therefore the most stable should be the sigma molecular orbital, this one. So I could call it as psi1. Next, there should be 2 pi's Further, in the antibonding side, pi star is more stable, should come down, and pi sigma antibonding should be the least stable. So this should be the highest in energy. Okay, this is how we draw the molecular orbitals. Now let's put signs here. Psi 1 having 0 nodes should encounter similar signs here. So this is the orbital shape. Psi 1 0 nodes, that means all the upper face p orbital should have same sign. Psi 2 1 node, this is corresponding to the molecular orbitals of butadiene. One node here, plus plus minus minus, this should be the shape of the orbital. If you work out here, Psi 3 having 2 nodes, so one is here, plus minus minus plus. Again see with even nodes, similar opposite terminal lobes, same face, have same signs. Okay, Psi 4 3 nodes, 1 2 3. Okay, this should be so this is plus minus plus minus, and finally, of course, this is minus plus minus plus, and finally Phi 2 star has 1 node. This is an anti-bonding orbital and counters different signs. So again we have to assign symmetry operations to this. I'll assign C2 and mirror again on this one. Okay, if you look at the mirror plane here, the mirror plane should be one which should be bisecting the molecule. So this should be the mirror plane, this should be the mirror plane, right? And if you look at the mirror plane, this orbital positive is encountering positive, therefore it should be symmetric. If this sigma orbital is symmetric, sigma anti-bonding should be anti-symmetric. It is simple. Okay, pi 1 positive encountering positive, positive encountering positive is symmetric, and then you have alternating axes of symmetry. This should be anti-symmetric, this should be symmetric, this should be anti-symmetric. This is how we've assigned the molecular the mirror operation onto these orbitals. And let's now assign the C2 operations. As I've told you, C2 axis should pass through this one, and should rotate at an angle of 180 degrees. Plus will come here, this plus will come here, will have similar kind of orbital, therefore this is symmetric. If this is symmetric, the sigma anti-bonding will be anti-symmetric, alternating symmetry. Okay. As far as phi 1 is concerned, we have to check the diagonal relationship. Plus is encountering minus, therefore it is anti-symmetric. Again, if this is anti-symmetric alternating, this should be symmetric, anti-symmetric, and symmetric. So we have assigned symmetry properties to the reactants, we have assigned symmetry properties to the product, we have drawn their molecular orbitals, and then if we are up to this step, the next step should be important for us. Therefore, in the next step, we would be considering how to, draw the orbital correlation diagrams for a conrotatory process as well as for a disrotatory process. So I'll start with the conrotatory process. First, under thermal conditions. I know for conrotatory process, again it is the C2 axis of symmetry which is to be chosen, right? Now while drawing the molecular orbital of the reactant, all I need to do is, again, you need to draw the Ocd diagram. This is psi 1, psi 2, psi 3, psi 4, psi 5 and psi 6. This is the 0 of energy. This is psi 1, psi 2, psi 3, psi 4 star, psi 5 star, psi 6 star, right? This corresponds to ground state or the bonding molecular orbital. This corresponds to the excited state. And this is the reactant side. What was the reactant? Reactant was cyclohexatriene. And on the product side, what was the product? Product was cyclohexadiene. On the product side, we have phi 1, psi 1 star, psi 1, psi 2, psi 3 star, psi 4 star, and phi 2 star. So it is phi 1, psi 1, psi 2, psi 3 star, psi 4 star, and phi 2 star. If you are talking about the thermal conditions, we have to accommodate 6 electrons of the reactant and accommodate 6 electrons of the products. First 2 will go to psi 1, next 2 will go to psi 2, and the next 2 will go to psi 3. In the thermal conditions, we do not expect an excitation to the higher orbital. Similarly, 2 electrons here, 2 electrons here, 2 electrons here. Now let's put the symmetry property. Which symmetry is to be chosen? Remember, in the coordinatory process it is the C2 which has to be chosen, right? Psi1 C2 was antisymmetric and then alternating symmetric, antisymmetric, symmetric, antisymmetric and symmetric. And as far as this one concerns, this was symmetric, this is antisymmetric, symmetric, antisymmetric, symmetric, and this was antisymmetric. This was the shape or the the symmetry properties of the reactant molecular orbitals when considering the coordinatory process. Now let's check the correlation. A correlates with A, perfectly alright. S correlates with S, perfectly alright. But here there is a mismatch. Therefore, I can say phi12, phi22, phi32 do not correlate with phi12, psi12, psi22. Hence, this reaction is thermally forbidden. Right? Because there is no correlation because there is a mismatch in the ground state. And while considering the photochemical processes or the photochemical process, that is the B part. Remember, while considering the photochemical process, all we need to do is we need to check the process up to the first excited state. Similarly, we'll draw the orbital correlation diagram. This side we have reactant, which one was what? Hexatriene molecule. On this side we have product, which was cyclohexadiene. This one again we need to draw the orbital correlation diagram. Let's say this is psi1, psi2, psi3, psi4, psi5 and psi6. Psi1, psi2, psi3, psi4 star, psi5 star and psi6 star. This corresponds to the zero of energy. Of course, this is the ground state and this one is the excited state. And here you have phi1, psi1, psi2, psi3 star, psi4 star, and finally the phi2 star. So phi1, psi1, psi2, psi3 star, psi4 star, and phi2 star. Again, the symmetry properties remain same as we discussed earlier. So it is antisymmetric, symmetric, antisymmetric, symmetric, antisymmetric, and symmetric. This one was symmetric, antisymmetric, symmetric, antisymmetric, symmetric, and antisymmetric. Now, since we are talking about the photochemical process, there will be an excitation of one electron from psi3 to psi4, and similarly there will be excitation of the valence electrons from psi2 and will go to psi3 star. And if we have to check the correlation up to first excited state, A matches with A, S with S, A with A, S with S. Even though there is a crisscross matching, the total symmetry operations of the ground state of the first excited state of reactant matches with the total symmetry operations of the products up to first excited state. Hence we can say psi1 2, psi2 2, psi3 1, psi4 star 1 correlates with phi1 2, psi1 2, psi2 1, psi3 star 1, and therefore this process is photochemically null. And as you can see, one process which is photochemically allowed should be thermally forbidden and vice versa. We'll talk about the distributary process now. While talking about the distributary process, everything remains same. The orbital shapes or the orbital remains the same. The only difference is that while undergoing a distributary process, the symmetry property which has to be considered is the mirror symmetry. Let's talk about first the thermal process and then we'll talk about the photochemical process. Now my reactant is and product. My reactant is again hexatriene. My product is cyclohexadiene. I have to write the molecular orbitals of the reactant. I have to write the molecular orbitals of product. Again, the same what we have done earlier. Psi1, Psi2, Psi3, Psi4 star, Psi5 star, Psi6 star. The zero of energy, the ground state, This one is the excited state. Product side we have phi1, psi1, psi2, psi3, psi4, phi2 star, psi1, phi1, phi2, phi3 star, phi4 star, and psi2 star. Which symmetry property has to be chosen? It is mirror. This was symmetric, anti-symmetric, symmetric, anti-symmetric, symmetric, anti-symmetric. Mirror was symmetric. This was symmetric, anti-symmetric, symmetric, anti-symmetric, and this was anti-symmetric. Now, since it is thermal process, I have to commute 6 electrons of the reactants. First 2 will go to psi1, next to psi2, next to psi3. Similarly, product side, 6 electrons have to be commutated. This should be the electronic distribution. So S matches with S, A with A, S with S. So ground state is correlating, and since ground state is correlating, I can say psi1 2, psi2 2, psi3 2 correlates with phi1 2, psi1 2, psi2 2. Hence this process is thermally allowed. And similarly, if I have to work out at the photochemical process, again everything remains same, only the difference is now we have to check the correlation up to first excited state. Again, I have to draw the reactant, I have to draw the product, and I have to draw the orbital correlation diagram. And in the OCD approach, this one was psi1, psi2, psi3, psi4, psi5, and psi6. The reactant side, psi1, psi2, psi3, psi4 star, psi5 star, psi6 star, the zero of energy. Again, this is the ground state, this one is the excited state, and in the product side, phi1, phi1 2, psi1 2, psi2 2, psi3 star, psi4 star, and phi2 star. So it is phi1, psi1, psi2, psi3 star, psi4 star, and phi2 star. Mirror, this is symmetric, anti-symmetric, symmetric, anti-symmetric, symmetric, anti-symmetric. Mirror on this side was symmetric, symmetric, anti-symmetric, symmetric, anti-symmetric, and anti-symmetric. Electronic distribution in the photochemical processes as one electron from the psi3 of the reactant jumps to psi4 star. Similarly, one electron from the psi2 of the product jump to psi4 star. We have to check the correlation up to first excited state, and when we check this thing, we find that S correlates with S, A correlates with A, S with S, but there is a mismatch at this position. That means at least even if there is one mismatch, we say that under photochemical conditions, the psi1 2, psi2 2, psi3 1, and psi4 star 1 do not correlate with phi1 2, psi1 2, psi3 1, and psi4 star 1. Hence, this process is photochemically orbital. Right? So this is a very lengthy but a simple way of gauging an electrocyclic reaction for its reaction conditions. Now the next task that you will attempt on your own is to gauge the OCD process for electrocyclization of octatetraene to cyclooctatriene molecule. This is a task that you should do for yourself. This will help you to understand the OCD approach for electrocyclic processes. Thank you.